Good morning, my dear students. We are continuing with the double indicator method of calculating and titrating, and today I hope that we shall finish this topic. Today we are looking at the last bit of the topic. As I've been telling you, this topic was divided into 3 sections, and in the first section we talked about the mixture of sodium hydroxide and sodium carbonate. The second one had a mixture of sodium carbonate and sodium hydrogen carbonate. We looked at this one using 2 methods, continuous, titrate, power. We looked at this one using continuous, then titrate and power. Very well. And today we shall look at the last one, which is a mixture of sodium hydroxide and sodium hydrogen carbonate. So that's what we're going to look at today. We are going to look at analysis of this mixture using the continuous method and then the titrate and power method. After that, I will be giving you some assignments and we shall be saying goodbye to that topic of double indicator. You will only be left to do a lot of practice. So our third mixture is mixture of sodium hydroxide and sodium hydrogen carbonate. We are going to look at these mixtures in 2 methods. The first one is continuous titration method. Continuous method or continuous titration method. In this case, you have your mixture of sodium hydroxide and the sodium hydrogen carbonate, maybe in a beaker. Then you prepare from this mixture using your pipette, which can be of 25 cubic centimeters or 20 cubic centimeters or 10. Then you transfer this mixture into a conical flask. So this will still be a mixture of sodium hydroxide and sodium hydrogen carbonate. Meanwhile, we have a burette containing an acid. Last time I showed you how we write equations involving all the acids when these substances are reacting with hydrochloric acid, nitric acid, and sulfuric acid. So there is no new equation here, though our simplest, which we shall use, will be hydrochloric acid because it is the most common one even. So here, after preparing your mixture in the conical flask, you add a few drops, 2 to 3 drops of phenolphthalein indicator to this mixture. Meanwhile, you know the volume, the initial reading of the burette. When you add phenolphthalein indicator, you will see a color change from colorless to purple. Then you start the titration. You titrate until when the color changes from purple to colorless. Then you stop. You read off the volume of hydrochloric acid or the acid that is used. You don't pour away this mixture, but instead what you do, you add another indicator, which is methyl orange, 2 to 3 drops. When you add the indicator, the solution you had turned colorless will now turn yellow. Then you note the initial reading of the acid. You have to make sure that the acid which is left in the burette is enough. If it is not enough, you top up with some more acid given. You continue titrating and note the volume of the acid required to reach the end point. The first volume here, we said we shall be calling it Vp, and then this one is called Vm. This is the procedure that we use in each of these mixtures is the same when continuous and the same when titrate and pour. So the most challenging part we need to talk about is how you do the calculation. But the good news is that this is the easiest mixture to analyze. I don't know why I even ended with the easiest mixture, because this one is very easy, as you will see. So we have only two reactions that take place during this titration. The sodium hydroxide, of course you should write the state symbols, but because I want to make these letters big and economize the space, I will not be writing the state symbols. But you should know that the state symbols are very important. So the sodium hydroxide will react with hydrochloric acid to form sodium chloride and water. The sodium hydrogen carbonate will react with hydrochloric acid to form sodium chloride plus carbon dioxide plus water. During the first titration using sonophthalin indicator, the color change, the end point will occur when only this reaction has taken place. So this is the reaction which requires the volume of acid, which we have called Vp. And then this reaction here requires the volume of acid called Vm. So it is very simple here that you see that the volume of acid required to react with sodium hydroxide is Vp, while the volume of acid which is required to react with the sodium hydrogen carbonate is Vm. So it is very simple as you are seeing it, just as simple as you are seeing it. Then the other method, which is called titrate, pour, titrate. This is my own name. The good thing is that they will not ask you about these names. You just need to know how to deal with these equations and then come up with the volume, the particular volume which is required to react with a particular substance. That's all that you need to know. So in this case you have your mixture. Again, the mixture is of sodium hydroxide and sodium hydrogen carbonate. You pipette from this mixture. It can be in a beaker. We normally put these mixtures in beakers. You pick your pipette. I'm not very good at drawing, but this one is a pipette. Then transfer into a conical flask. So the mixture you have transferred therefore is of sodium hydroxide and sodium hydrogen carbonate. Meanwhile, you have your acid. You have your acid. No, this is a burette. You have your acid, which is, let's say it is also HCl. So you add the first few drops of indicator, phenolphthalein. The color change will occur, and you stop there when the color change occurs during the titration. Then you can pour this mixture away and wash the conical flask. Or if you have two conical flasks, you pick the second conical flask. You go back to the original mixture and pipette another sample. This mixture formed after this endpoint is useless, so you can pour it away. In fact, it is very good to pour it away because since it becomes colorless, it may confuse you and you end up picking it again for another experiment, yet it is used up. So it's very important that during the titrate pour titrate mixture, after getting the first endpoint, you pour away that mixture because it's no longer useful. Now you come back and pipette from the mixture. Meanwhile, you have your burette and a conical flask. So when you prepare this mixture, you transfer it into a conical flask. So this one is a mixture of sodium hydroxide and sodium hydrogen carbonate. This is your burette containing an acid, e.g. hydrochloric acid. As I've been telling you, this can be nitric acid or sulfuric acid. Not always be hydrochloric acid. However, the hydrochloric acid is the most commonly used acid. But when you are learning, you should learn about equations for all the acids. So here, you add a few drops of methyl orange indicator and titrate. Here we note the volume VP and here we note the volume VA. How do you treat the results? How do you treat the results? We have two equations here. Let me create some space here. So this one we said is a mixture of sodium hydroxide and the sodium hydrogen carbonate. So we shall have two reactions. Sodium hydroxide reacts with hydrochloric acid to form sodium chloride and water. Then sodium hydrogen carbonate will react with hydrochloric acid to form sodium chloride plus carbon dioxide plus water. The color change here will occur when this reaction has taken place. So we call that volume VP. And then in the second titration, now you have a fresh sample containing both. So VM will be for both reactions. VM will be now for both the reactions. Let me write this again so that you can see it very well. For the titrate pour titrate mixture, sodium hydroxide plus hydrochloric acid gives us sodium chloride plus water, whereas sodium hydrogen carbonate will react with hydrochloric acid to form sodium chloride plus carbon dioxide plus water. I said that in the first titration, this is the volume of acid required, and then in the second one, since you are dealing with a fresh sample, the volume will be for both reactions, and we shall call that one VM. So, volume of acid so this one alone will be VM minus VP. Volume of acid to react with the sodium hydroxide is VP. while volume of acid to react with the sodium hydrogen carbonate is Vm minus Vp. Whereas here, the volume of acid to react with the sodium hydrogen carbonate is very clear, Vp. Volume of acid to react with the sodium hydrogen carbonate is also very clear as Vf. That's why I was telling you that this one is the easiest mixture to analyze. The hardest mixture is the mixture of sodium carbonate and sodium hydrogen carbonate, which we looked at in our previous lesson. So once you get to know these volumes, now you can be able to do the calculations. Let us look at some of these calculations which we have. For example, the calculation which you have on page 48 here. We have 25. From that calculation, now you also need to train yourselves to be able to analyze a question and see, first of all, what type of mixture it is, and then is it continuous or titrate, poor titrate? Because these numbers are also set in theory exams, and they do not tell you that this is a mixture analyzed by titrate, poor titrate, or continuous method. But by reading through the question, you should be able to know the type of method which has been used or which is being used in that analysis. Our example of page 48 here reads, I will not read through it. I know you have the work, have the notes. But when you look at this example, the method being used is the continuous titration method. And our Vp, first of all, volume of pipette was 25 cubic centimeters. Concentration of acid 0.1 molar. Vp equals 16.70 cubic centimeters, and then Vm equals Vm is 9.50 cubic centimeters. So from here you can find out volume of acid to react with the sodium hydroxide is equal to, which is our Vp, equals Vp, and our Vp is 16.70. Then we can be able to calculate the number of moles of the acid, the molarity of the acid, and hence the concentration in grams per liter of the same acid. So from this information, let's begin with the sodium hydroxide. 1,000 cubic centimeters of acid solution or HCl solution contains 0.1 moles of HCl, or about 16.70 cubic centimeters. 0.1 times 16.70 over 1000 moles. What we get here will be 0.00167 moles of HCl. And when we look at the reaction between sodium hydroxide and hydrochloric acid, the mole ratio is 1:1. Mole ratio of sodium hydroxide HCl equals 1:1. So meaning that 1 mole of HCl reacts with 1 mole of sodium hydroxide. Therefore, 0.00167 moles of HCl react with 1 times 0.00167 over 1. This gives us the same number. Even when you know that the answer will be the same, you need to show that working, because you earn extra marks when you do it. This number of moles were in this pipetted volume. So you said 25 cubic centimeters of mixture contain 0.00167 moles of sodium hydroxide. What about 1000 cubic centimeters contain? This will be 0.00167 times 1000 over 25 moles. And on analysis, we realize that from this we get the concentration of sodium hydroxide in moles per liter as 0.06680 moles per decimeter cubed. From this one, you can be able to calculate the concentration in grams per liter of that substance. I'm very sure you can be able to do that. So, this assignment, first assignment I'm giving you is to go and complete that part. Then we also go to the mixture of we go to the other component, which is the other component is sodium hydrogen carbonate, volume of acid. That was required to react with the sodium hydrogen carbonate was Vm. Very simple. So it is simply 9.50 cubic centimeters. So again, you start and say that 1000 cubic centimeters of HCl solution contain 0.1 moles of HCl. What about 9.50 cubic centimeters? These ones contain 0.1 times 9.50 over 1000 moles of HCl. From this you get 0.00095 moles of HCl, hydrochloric acid. At this point you write the equation of reaction. Sodium hydrogen carbonate reacts with hydrochloric acid to form sodium chloride plus carbon dioxide plus water. What's the mole ratio of the reaction? Mole ratio equals 1 to 1, meaning that 1 mole of HCl reacts with 1 mole of sodium hydrogen carbonate. What about these moles? 0.00095 moles of HCl react with 1 times 0.00095 over 1 mole of sodium hydrogen carbonate. So the number of moles of sodium carbonate is 0.00095 moles. From this one, you can be able to calculate the molarity of the sodium hydrogen carbonate, which I know you can do very well. At least I've been interacting with you. You can get the molarity from these moles by saying that the 25 cubic centimeters of the mixture contain these moles. What about 1000 cubic centimeters? What do they contain? When you do that, you can get the answer. Then from the molarity, you can be able to calculate the concentration in grams per liter of sodium hydrogen carbonate alone. From there, you say, because the mixture was 25 cubic centimeters, you say 25 cubic centimeters of mixture contains 0.00095 moles of sodium hydrogen carbonate. What about 1000 cubic centimeters of the same mixture contain? And you cross multiply 0.00095 times 1000 over 25 moles. What you get here will be the molar concentration of sodium hydrogen carbonate alone in the mixture. Using my calculator here, I can say 0.00095 equals 1000 divided by 25. I get 0.038 molar From this, you can calculate the concentration in grams per liter by using the RF. First of all, you calculate the RFM. When you get the molarity, it becomes very easy for us to calculate the concentration in grams per liter, and I'm very sure my students can do that. I don't want to waste time on it. So that has been the example about the mixture of sodium hydroxide and sodium carbonate using the continuous titration method. Then we can also do this calculation, which is on page 49, where we are changing the method now, and we are using the titrate pour titrate mixer. But before we go there, I want you to try out this exercise, which is on page 49. This is experiment 4.5. You need to get a pen and write this. Volume of PET, so we are looking at page 49. The volume of PET used is 25. Then average volume of Fa2 using to write 16.65 cubic centimeters. I hope we are doing it. And then average volume of Fa2 used in table 2, you write 9.25 cubic centimeters. Then you will be able to go through that calculation during your free time. I saw you sharing your answers, your findings on our WhatsApp group, and that's very good. I must commend you for that. So you do the same even here, and then get an answer. Get your answers, try to compare with those of your friends. You can use our forum, the WhatsApp group we have. Then let's also do this example, which is on page 51. The information there can be summarized as follows. Volume of PET which was used, or the volume of the mixture, was 25 cubic centimeters. Concentration of the acid is 0.2 molar. Then Vp is 15.00 cubic centimeters. Then Vm is 29.00 cubic centimeters. So from there, we are being asked to calculate the concentration of sodium hydroxide and then sodium iodine carbonate in the mixture, the concentration in grams per liter. So we can begin with the sodium hydroxide and say volume of acid that reacted with sodium hydroxide alone. This volume, according to our analysis, it is Vp, which Vp is 15.00 centimeters cubed. So we start from there and say 1,000 cubic centimeters of HCl solution, which is the acid solution, contain what the molarity of the acid was. It is 0.2 moles of the acid, which is HCl. What about this volume? 15.00 cubic centimeters contain 0.2 times 15.00 over 1000. Using my calculator, I get 0.003 moles of HCl. Then I write the equation of the reaction. Sodium hydroxide mole ratio. Don't forget to put the mole ratio. Sodium hydroxide to hydrochloric acid is equal to 1 to 1, meaning that 1 mole of hydrochloric acid reacts with 1 mole of sodium hydroxide. What about 0.003 moles? These ones will react with 1 times 0.003 over 1 moles of sodium hydroxide. What you get will be 0.003 moles. Then these moles were in 25 cubic centimeters. So it's 25 cubic centimeters of mixture. Which mixture? A mixture of sodium hydroxide and the sodium hydrogen carbonate contain 0.003 moles of sodium hydroxide. What about 1000 cubic centimeters contain 0.003 times 1000 over 25 moles. The concentration of sodium hydroxide equals 0.12 molar. But they are asking for the concentration in grams per liter, which I know very well that you can do, but okay, we will do it. Start by getting the RFM of sodium hydroxide. 23 plus 16 plus 1, that is 40. So you say 1 mole of sodium hydroxide weighs 40 grams. About these moles. Cross multiply 40 times 0.12 over 1. What you get here will be the concentration in grams per liter. So this will be 4.8. So the concentration 4.8 grams per liter. So this mixture has 4.8 grams of sodium hydroxide per liter of solution. The other substance, the other component is sodium hydrogen carbonate. We can also calculate, we can also determine its amount. So we can go to Roman 2. And say, now we are dealing with the sodium hydrogen carbonate. They say that volume of acid that reacted with the sodium hydrogen carbonate, according to this mixture, this is a titrate for a titrate mixture. So this will be Vm minus Vp, and therefore we shall have 29.00 minus 15.00. This gives us remaining with 14.00 cubic centimeters. That's where you say that 1,000 cubic centimeters of HCl solution contain 0.2 moles of HCl. What about 14.00 cubic centimeters? Contain 0.2 times 14.00 over 1,000 of HCl. From the multiplication, we shall get 0.0028 moles of HCl. After that, we write the equation. Sodium hydrogen carbonate reacts with hydrochloric acid to form sodium chloride plus carbon dioxide plus water, and the mole ratio of sodium hydrogen carbonate HCl equals 1:1, meaning that 1 mole of HCl reacts with 1 mole of sodium hydrogen carbonate. So what about 0.0028 moles of HCl react with cross multiply so you get 0.0028 moles of sodium hydrogen carbonate. But these moles were in hydrogen carbonate. What about 1,000 cubic centimeters? Contain of the same mixture 0.0028 times 1,000 over 25 moles. The answer which you get here is 1 be the concentration of sodium hydrogen carbonate, and it is 0.112 mole. So at this juncture you get, you capture the RFM of sodium hydrogen carbonate is 23 plus 1 plus 12 plus 16 times 3, get 84. And say 1 mole of sodium hydrogen carbonate weighs 84 grams, about 0.112 moles, weigh 84 times 0.112 over 1. What you get here will be the concentration in grams per liter of sodium hydrogen carbonate alone in the mixture. This is 9.408 grams per liter. So after doing that number, I want to give you another exercise. When you open page 51, that 4.6 experiment, we shall use a pipette volume. I hope you are following. We shall use a pipette volume of 25. Then VP, we shall use a VP of 14.45 and a VM of 28.5. You go through that work and make sure that you get the answer. Now we have a UNEB number that is on page 54, a past paper number. It's a full exercise. I want to give you the values, the volume which we will base on to do this calculation. I want you to turn to page 54 and fill in the following. Volume of pipette, we shall fill in 25.0. Volume of pipette, we are filling in 25.0. Then average volume of FA1 used, still on page 54, average volume of FA1 used, you write 12.50 cubic centimeters. The volume of pipette was 25.0 centimeters cubed. The average volume of FA1 used in table 1, 12.50 cubic centimeters. Then below there, they are asking you to determine the molarity of Fa3. You will work it out. Then they are also asking you to get the molarity of Fa1. You should work it out as well. Then we turn to page 55. There is that volume of pipette used. You write 25.0 centimeters cubed. Then you'll also have to fill that table very well. Try to fill that table appropriately. Then the average volume used with phenolphthalein, we shall take the VP as 6.25 cubic centimeters. That is the VP. VP is 6.25 cubic centimeters. The VM is 12.55. The average volume used with methyl orange, you will take 12.55 centimeters cubed. Then on part B, you will work that one out on your own. I will not give you the values there. You can work them out on your own. I don't want to give you the answers. You will calculate on your own. Then you will tell me the answers which you will get on the WhatsApp group. Then the topic has ended there, but I want to answer some of the questions which you have been asking about all this. There is something which I didn't tell you, and I did this intentionally because it wasn't necessary at that time. It was going to simply confuse you. The explanation, why is it that, and one of you asked me that question. That's very good. Mbogo Mahad asked me that question, that why is it that phenolphthalein indicator changes in color only after converting sodium carbonate. You know, sodium carbonate is neutralized in two phases. You have from sodium carbonate to sodium hydrogen carbonate, then from sodium hydrogen carbonate to sodium chloride. Now, Mbogoma had asked me, why does the phenolphthalein indicator, I wanted to know, why is it that phenolphthalein indicator changes color only up to this reaction and not up to the end? Why is it like that? Now, what I told you in this in our introduction of acid-base indicators, these indicators, phenolphthalein indicator and methyl orange, is that they have what we call working ranges. Working range of methyl orange indicator, and then we have working range of phenolphthalein indicator. If you have your book there, you can open page 8. The working range of phenolphthalein is 3.0 to 4.4, while that of phenolphthalein is 8.2 to 10.0 pH. These are pH values. We define working range as the range of pH values under which the indicator changes the color. Now, when you are titrating sodium carbonate with an acid, the reaction takes place in two phases. In the first phase, as you add an acid to sodium carbonate, it starts being converted to sodium hydrogen carbonate. When all this is converted, when all the acid is converted to sodium hydrogen carbonate, the pH of that solution is still low. Is low. Because at the beginning the pH is high, and as you add in an acid, the pH starts to what? To decrease or to lower as you add on an acid. But when you look at the pH patterns, sodium carbonate, sodium hydrogen carbonate, then sodium chloride. In the first phase, the pH lowers. This pH here is lower than the pH of the solution of sodium hydrogen carbonate is lower than the solution, that of the solution of sodium carbonate. But this pH here, the pH of the solution, will still be below. Will still be above 4.4, which is the range, which is the higher limit at which the indicator changes color. So it's only phenolphthalein indicator which can show a color change, because this pH of the solution here is still above 4.4. When you continue adding the acid, that's when the pH lowers again, and that's when it goes below 4.4. So in that case, the color change will only be formed of methyl orange when you are dealing with, the only range where you see the color change is when you are using methyl orange. This part here is a bit confusing because there are certain terms which I don't want to mention here before we study the topic in detail of acid-base titration. I think to understand this in detail or very well, you have to be patient until when we study acid-base titrations in physical chemistry. But right now it may not be easy for you. I've been challenged always to make students understand this before they do the other topic of acid-base titrations of seniors. This is a topic which we normally teach in senior 6. But what you need to know is that it's all about working ranges, and that by the time we form sodium hydroxide, the pH of this solution dictates that phenolphthalein indicator will change color, but when you add methyl orange, it will not be changing color. I want you to make sure that you do those assignments which I've given you, and when you do the assignments, try to share your answers on the WhatsApp group. Some people are very quiet on the WhatsApp group. It's only, normally I see Brittany who shares answers with us. Brittany, another person who shares answers with us. Let me check here. People who share their answers with us. Others just continue writing funny things. I will not mention your names, but please use this group for academic purposes. It will even take time to see something. For example, here, Labna was sharing the answers. That's very good. Then Waswantare also. Waswantare, Chico, Akram, Labna. These are the people who do serious academic work. Then we have Nabatesa Shina. She also does academic work on the WhatsApp group. They are using this group for academic purposes. We have again Waswa, Ntari, Nabatesa Shina, Nalima, Brittany. These are the people who use this one. Coral Sain. There is this one called Shina. Then we have this one called herself Trisha Oki. These are the people who use this WhatsApp group very well. Nabatesa again, Nabatesa Shina. Please, members, use this WhatsApp group for academic purposes rather than concentrating on funny things. Remember, we don't have a lot of time. We don't know when you people will be doing your enable exams. At first it was March, but maybe it will be changed slightly. But still, the time will not be enough for you. I'm ending here and wish you the best. Juma Mubarak. Assalamu alaikum wa rahmatullahi wa barakatuh.